Hmm. So purification of organic molecules. Have you done any experiment to purify two compounds in a mixture or isolate some natural product from and then purify it in your lab experiment in organic chemistry? Was there any experiment based on chromatography? I think last time I did, I think I asked that. And there is some knowledge about chromatography. It appeared that the small molecules, yes, someone wants to answer. So you have some exposure to chromatography techniques? Yes, sir.
Yes,
Um,
sir.
okay, good. Now, in see, when you have two organic molecules, small organic molecules, the organic molecules are usually uncharged unless they are basic or acidic. Otherwise, they will be uncharged molecules, and the majority of the compounds are uncharged. They do not possess any charge. So the but what is the difference between two compounds, or what could be the differences? One difference could be what is called their polarity. Their polarity, that there may be a lot of polar functionalities in one molecule. In the other molecule, there may not be that many polar functionalities. So there will be a difference in the polarity of the samples. Uh, how does it affect? The polarity basically gives the molecule the ability to attach to another polar molecule by charge-charge interaction. Okay, so that interaction will be different for two molecules. If suppose I have two molecules A and B, sorry, A and B, and their polarity is different, and polarity is different. So what will happen? That if I add add some solid in both the systems, a solid which is suppose slightly polar, has some polar character, then what will happen? That there will be greater interaction between this solid and the compound A, provided the compound A is more polar than compound B. So this is one scenario. One scenario means when the two compounds that are going to be separated, they polarity, differ in polarity, and this is actually exploited in chromatography. That what is done in there are various types of chromatography. One is called the column chromatography. So what you do, you basically take this solid, what I am saying here, take the solid and add these two compounds. You absorbed, you get it absorbed on the surface of the solid, and then you add some solvent, and the solvent drops down. And what will happen? There will be always a tussle. The solvent will try to take these compounds along with it as it goes down, but the solid will also have affinity for A and B, so there will be a tussle now. The solvent will interact with A, solvent A interaction, that will try to take the compound A along with the solvent as it goes down, and so also the solvent will interact with B. Okay. Now, if the interaction of B with this solid is less, then what will happen? The solvent can uh, take this molecule B along with it faster than the compound A. Basically, that is what usually we say, that B will move faster as compared to A, because A is more tightly bound to the solid. Why it is more tightly bound? As I said, A is more polar. So due to the polarity, it gets stuck to the solid, and the solid has also is also slightly polar. If the solid is totally non-polar, then the situation will be different. But here we are thinking that the solid is slightly polar. So then this will interact. Like charges will, unlike charges will associate together, so that the interaction will be here more. So basically, that is the principle of chromatography, that you have some solid matrix, which is basically called a stationary phase. A stationary phase, and the liquid that you are dropping from the top, that is called the mobile phase, because that is what is moving. Mobile phase. Yes, someone wants to say anything?
So can you explain the concept of how it works once more?
Okay. Basically, what I'm saying, that I suppose I have this type of a glass column, like a burette, basically like a burette. Only the diameter is much more than a burette, and then you pack with a solid, which is on to top of which you are actually adding the compound A and B in as a solution, and it should be in as thin layer as possible. Means when you add the solution of A and B, you add, suppose you try to minimize the volume. Slowly, you add the drops, add in drops, and allow the solvent to evaporate. So what will happen? The upper portion of this solid bed will be covered by A and B. The solvent has gone out. Slowly it will evaporate. So leaving the A and B adsorbed, not absorbed, adsorbed on the surface of the solid. Okay, so of the solid. Now what what is generally done is, now you add a solvent from the top. Okay, now the solvent will under gravity it will go down, and ultimately you can collect it in suitable containers, in test tubes or in conical flask, whatever it is. Now basically what happens when you add the solid, when you add the solvent also has interaction with A and B, and that interaction will also be different, because the polarity different in polarity of A and B. Okay, so then what will happen, as the solvent goes down, the solvent wants to carry with it A and B as it goes down. Okay, and the solid, that is what is the bed is packed, the solid bed, that wants to retain A and B along on its surface. Okay, or that wants to have this A and B adsorbed on the solid. Okay, so basically there are two forces. If you look again, like basically what is happening, there are two forces that are acting. One is solvent and the compound, and the solid bed and the compound. Okay, since there are two compounds, A and B, so interaction solvent interaction with A will be different than the interaction of the solvent with B. So also the interaction of the solid bed with compound A and with compound B will be different. So that actually what happens, that results in differential migration of A and B along the when the solvent is going down, both A and B will will also come down along with the solvent, but at a different rate. Why at a different rate? Because as I said, the solid, like between A and B, if A is more polar than B, then which one should come faster? Between A and B, which one should migrate faster or come down faster than which one will come down faster, A or B? Then I will realize that you have understood the issue. See, basically A and B will try to also go down along with the solvent, but the solid wants to retain A and B by this interaction, polar interaction. Because A is more polar, the solid will retain or will try to slow down the movement of A as compared to B. Is it clear now? Is it? See, give an example. Suppose I have two compounds. One is suppose a phenol, and the other is a carboxylic acid. I have a mixture of these two. I want to separate them. Which one is more polar between these two? This is carboxylic acid. This is a weak acid. So definitely this is more polar. And this is less polar. Okay. So when I have a mixture of these two on the top of this bed, of the solid bed, and then add the solvent, the solid bed, because of its more interaction with the carboxylic acid, so carboxylic acid will move slower because this solid wants to retain it, because of a larger force acting between this benzoic acid and the solid. Okay, so the phenol will come faster, will move faster than the carboxylic acid. Okay, so basically what you are exploiting the character, the polar character of A and B, and that will allow you to separate the two molecules. But suppose the two molecules are having almost same polarity, then what are you going to do? Then it will be difficult to separate them, which is actually true when the compounds are very similar polarity, then their migration ability. Migration means as it comes down from the top to the bottom, that also are very similar. So in that cases, you have to be very careful. Means you have to, if there is a slight difference in polarity, so you have to use a solvent very carefully. You have to choose the solvent, that is, you are dropping from the top of the bed very carefully, so that slight polarity difference you can exploit. If there is a large difference in polarity, that separation will be very easy. If there is a small difference in polarity, the separation will be difficult, not impossible, but difficult. Like suppose again, you know what is called RF, by the way? RF value. RF value is basically another type of chromatography that we do is called thin layer chromatography. I don't know whether you have done it or not. So you have a glass plate, which is, you have done it? Hello?
Yes, sir.
Yes, nah? So what is RF? Basically what you do, this is coated with a solid matrix, usually silica gel. Okay, so what you do, you put the compound, drop a solution of the compound here, allow the solution to dry out, and allow the compound to become dry. So the compound is stuck to or adsorbed on the silica gel surface. Now you put it in a chamber. You put it in a chamber, and the chamber is filled up with a solvent up to this point. So below the spot, below the where the you have spotted the compound. Okay. So now what will happen? Because of capillary action, the solvent will slowly go up, like a blotting paper. If you put a blotting paper here, and ultimately what will happen, the solvent will slowly go up by capillary action, and suppose when the solvent almost reaches at this point, you take this plate out. Now what is the effect of solvent when it goes up? It will try to take this solid along with it, but the silica gel wants to retain it at its at the place where it was. Okay, so there is a tussle between the solvent solid interaction and the matrix, that means the silica gel solid interaction. So ultimately what will happen, this will move, but this will move at a pace uh, which is dependent on the relative differences between these interaction. Okay, so when you take this plate out, you will see that this compound has migrated, say, up to this point. Okay, and then we calculate what is called the RF value relative to front. That means I have allowed the solvent to go up to that point. So basically I measure the migration of the solvent by a scale, so that is up to this point, and I measure the migration of the compound, which is now at this point. So these two, x by y, is what is called the RF. That means relative to the front, this is the solvent front, which the solvent has gone up to that point, how much the compound has migrated. That is what is called the RF value. So this RF value actually is a measure of the means which compounds will have higher RF value. Basically compounds which are less polar, because then it will have less interaction with the silica gel. Which compounds will have low RF value, that means movement is slow. The compounds which are polar, because they are having greater interaction with the silica gel, so their movement will be, or migration will be, slower. Okay, so now what happens, suppose you have a mixture of two compounds. If the two compounds, you see that the solvent you have used here, and when you take the plate out, the two spots are, suppose one spot is here and another spot is here. That means there is a large difference between the RF value. But sometimes what it can happen, that there is very small difference in the RF value, that one compound is here and another compound is here, very close by. Then you have to be very careful. Careful means if you want to separate these two molecules, then you have to do it in a very slowly. Slowly means another point, the solvent that I was using, I can also change the polarity of the solvent. If I use a solvent which is more polar, this is another question. Suppose I have a compound A which has got an RF value of 0.4, say, in hexane. Hexane as the solvent. Okay, the hexane going upwards. Okay, there is a name. I will say that is called that is the mobile phase. I already told you this, the one which is moving, that is called mobile phase, and the other phase is basically this silica gel coated on the plate, which is not moving, which is actually stuck to the glass plate. That is called a stationary phase. Okay, so if you are using hexane and you are seeing that RF of a compound is 0.4 in hexane, then if I use, suppose, methanol now, as the mobile phase, then what will be the RF? RF will be greater than 0.4, or RF will be greater or less than 0.4. Who can answer this? Using the same type of plate, that means using the silica gel coated plate. I am just changing the polarity of the solvent. If I use less polar solvent, that means hexane, I see an RF of 0.4. That means it has migrated 40% relative to the front. If I say that the front has migrated by 100%, then at the 40% distance, it has migrated. Okay. If I increase the polarity of the solvent, methanol, what will happen? The RF value will increase or decrease?
Decrease.
That is, it will
Decrease.
Decrease or increase?
Decrease.
Increase or decrease?
Decrease.
Decrease, you are saying. Why you think that it will decrease? See, you have the, again, look at this. See, I have said that there is always an interaction. There are two interactions that are going on. Okay. The interaction is between the silica gel, that means the stationary phase, and the solid compound versus the solvent and the solid compound. Okay. So when you have more polar solvent, the interaction of the solvent with the compound will be more, because they are increasing the polarity of the solvent. Okay. If you decrease the polarity of the solvent, then the interaction of the solvent with the or the mobile phase with the solid will be less. Okay. Now again you rethink that if I increase the polarity of the solvent, that means the silica gel, the interaction of the silica gel with the compound is now slowly losing out. Is now slowly losing out because the interaction, the other interaction, the solvent solid interaction is more, because the polarity is more. The solvent has more polarity. So now the compound will move at a faster rate than when it moved in a solvent which has got less polarity. Who was that answering that question? That you said decreased, but actually it is increased. As you increase the polarity, RF will increase for silica gel chromatography, not for all type of chromatography. For silica gel chromatography, that means chromatography where polarity is important. Again, I hope it is clear. See what I am saying, that because you are using a polar solvent, so the interaction of the solid with the polar solvent is now more. So the solvent will take along with it the compound at a faster rate than when you are using hexane, because hexane is less polar. So the interaction of the compound with hexane is much less, and the interaction of silica gel with the compound is now will be more. More means it is larger than the interaction with the hexane. So it will move slower. Is it more or less okay?
Yes, sir.
Yes, sir.
Okay. So now let's see if it is now, as I was telling, that if there are two compounds which are very close to each other in RF, in a particular solvent, okay, in a particular solvent they are very close to each other, then their separation will be difficult, okay, but not impossible. If there is any separation, you see here, any separation, they can be separated, but you have to be very careful. Careful means what you do, you start with a very non-polar solvent. As I have said, in a non-polar solvent, the movement of the compounds will be much less in a non-polar solvent. In a polar solvent, they move faster. Okay. In a polar solvent, they move faster. Okay. Now suppose you have a 100. Suppose there is a 100-meter race that happens in Olympics, in many in sports event, 100-meter race, and suppose there is a 5,000-meter race. Both actually are events in Olympics. In 100-meter race, if you have watched that, it appears, when you see in the television, it appears that many people are almost, they come so close one after another that it is very difficult just to visualize that who is the first one to come at this point and who is the second one, who is the third one. Fortunately, we have electronic clock, and that we call a photo finish, means they take the photo and then along with the clock. So ultimately, they can distinguish that who has actually reached the point faster than the other. Even a fraction of a second, they can distinguish. But that is the technique which is called photo, is which you use an electronic clock along with photos. You take snaps at every point, and then ultimately you can get that who has come faster, who has reached this point faster than the other. Okay. Usually what happens in a 5,000-meter race, you will not see that. You will see that one fellow has come first, and then after few seconds, another fellow comes second, then another few seconds, the third fellow has come. That means there is a gap in time between A, B, and C, if these are the participants. Okay. The gap in the time difference between ABC for a small race is much less than the gap between the timings as the gap between the timings as the total distance increases. Like in a marathon, if you have a marathon race, there is no such problem, because one fellow comes about, say, 15 minutes earlier than another fellow. Okay, so you never have any problem that who is first, who is second, who is third. So basically what I am telling, that as you increase the total length that has to be traversed, that has to be covered, you actually make more differences between A, B, and C. As the distance is smaller, then the gap between A, B, and C, the gap in timing of reaching the end point by ABC will be very less, fraction of seconds. Okay, so it's the same thing here. See, what you have to do, you have to start with a very non-polar solvent so that they slowly move, these two compounds slowly move. And if they move slowly, so what will happen? Ultimately, their gap increases between the two. So when they reach at this point, then one compound, if one compound is here, the other compound may be is following much behind than the other. Basically what I'm saying, as you slow down the movement, like you can do it in a 100-meter race. Suppose you are taking there is a race between A and B, but A moves much faster than B. Then the timing, the gap in the timing will be much more. Okay, but if they both move very fast, then the gap in their timing will be much less. Okay, here what you are doing, you are actually making both A and B to move slower, but as they are moving slower, so what will happen? Ultimately, they will have the gap between the two will slowly increase. Their difference will slowly increase with time. Or the Other one is that you make the plate very big, a larger plate, like this comparison between 100 meter and 5000 meter. If you make a larger plate, a larger distance to travel, then these two spots which are earlier very close, now they will be, if one is here, the other may be at this point. Okay, simply because they are traversing at a larger distance. Okay, so this is the principle of chromatography. Okay, now in case of proteins, okay, in case of course, here another point I should mention. Suppose these two molecules, the molecules that I am trying to separate, they have similar polarity, but their molecular weight are widely different. If the molecular weight are widely different, then also the movement along this plate will be different. Like obviously, a person who is basically having a body weight of say 100 kg, and a person who is having a body weight of 60 kg, obviously the 60 kg fellow will run faster, it is expected, will run faster than the 100 kg fellow, right? That means that is basically a comparison of two molecules with different molecular weights. If the molecular weights are widely different, then also you can exploit the molecular weight difference to control their movement. So what I am saying, that there are two ways to control the movement. One is by exploiting their polarity difference. Another is by exploiting their difference in molecular weight. Okay. In case of proteins, proteins are made up of what? Amino acids joined together. Okay. And amino acids have side chains. The side chains have basic groups as well as acidic groups, as well as OH, SH, those type of polar functionalities. Okay. So ultimately what will happen at a particular pH, a protein will have a definite charge. It could be positive, or it could be negative, or it could be neutral also. It could be neutral. That means the number of positive and negative charges counterbalance each other. Okay. Now what is that pH called? That where the molecule is electrically neutral, in case of amino acids or in case of proteins, that is what is called isoelectric point. Last time I told you, isoelectric point is basically nothing but a pH where the protein or the amino acid is neutral. If it is neutral, it will not move in an electric field. If you apply an electric field, then what happens? If the protein is positively charged, it will move towards the negative direction, negative electrode. If the protein is negatively charged, it will go to the positive electrode. Okay. Or if the proteins have different extent of positive charges, that one protein at a pH say 5, one protein has 5 positive charges, excess, and another protein has only 1 positive charge, excess. Okay. So when you apply a field, what will happen? Both will move, but the one which has got more positive charges, that will move faster than the other. Okay. So in case of proteins, separation of proteins, how many factors you can exploit to separate the molecules? Like in case of organic molecules, I told you that the two things which are exploited are basically polarity and molecular weight. Okay. In case of proteins, you have some other extra parameter that can be exploited to separate proteins. One is based on the molecular weight, which is understandable. That heavier molecules will move slower, and lighter molecules will move faster. Okay. Another is based on the charge. that molecules with higher charges, whether it is suppose positive charges, they move faster. They will move faster than in comparison with a molecule with a lower extent of charge. Okay, so you can exploit the charge because different proteins have different isoelectric point. So their extent of positive or negative charges at a particular pH will be different. Okay. Then the third point that also you can exploit, that is called solubility. The solubility, of course, this is also solubility can also be exploited in organic chemistry. That when you have you can separate two compounds by crystallization, what is called fractional crystallization, where you exploit the solubility parameter of the two compounds. So same thing can be done for proteins. The proteins are usually soluble in water, but their solubility is affected by dissolved dissolved solutes like ionic solutes like sodium chloride, ammonium sulfate, like different ionic compounds. Okay, that will affect the solubility of the protein, and that will affect the solubility of the protein to different proteins to different extent. Okay, so basically what I am saying, that if you have a solution of proteins in a, say in water, if you add a polar solute like say ammonium sulfate, okay, you add suppose 1 milligram, and you see that okay something is precipitating out. That something is one protein, particular protein which will precipitate out. Okay, as you increase the ammonium sulfate, more and more proteins will precipitate out. So by controlling the amount of this ammonium sulfate, you can selectively precipitate out proteins. That means it is very similar to your fractional crystallization in organic chemistry. Okay, so this is what is called you are exploiting the solubility parameter of a protein in presence of an ionic solute. Okay, and the fourth thing is what is called affinity. Okay, affinity, I will discuss what is this affinity means. Affinity means actually the interaction between two compounds, that a compound has affinity for something, like if we say phosphorus has higher affinity for oxygen because of the strength of phosphorus oxygen bond. So many times we use this word affinity. Affinity means basically the interaction between two entities. Okay, if the interaction is high, then I will say that they have better affinity between themselves. If the interaction is low, they have weaker affinity. Okay, so you can exploit that affinity also to separate the proteins. So basically there are these four parameters are utilized for separation of proteins. Okay, remember, protein separation is much more difficult than separation of organic compounds. Okay, because you are actually handling these molecules in proteins are usually soluble in water. Organic compounds are soluble in organic solvents, where you have many choices. Organic solvents, you can have hydrocarbon solvents, hexane, dichloromethane, chloroform, methyl acetate, benzene, toluene. So there are large number of organic solvents with different polarities. So separation of organic compounds are, this is also organic compound proteins. I am saying, when I say organic compound, means this is small organic molecules. So their separation is easier than the separation of proteins. However, there are techniques. It is difficult, more difficult than organic molecules, but it is possible. Proteins can be purified with the help of these four parameters: molecular weight, charge, solubility, and affinity. So let us discuss one by one what are these things. Okay, something is written here: processes based on molecular weight, separation processes based on molecular weight. This is what is called gel filtration, very similar to your column chromatography, but I will discuss where is the difference. And the other is says SDS page separation. SDS page we will have to discuss these two. Okay, gel filtration. Let us. Let us. We can actually first come to the separation. Separation based on molecular weight are these two: gel filtration, SDS page. Separation based on solubility is what is called salting in and salting out. I will just discuss. Let us just talk about the techniques that are based on this. Separation based on solubility is salting out, salting in. Separation based on molecular weight is gel filtration, SDS page. Separation based on charge is again is what is called. There are different chromatographies. Again, whether you have heard this ion exchange chromatography. Do you know anything about ion exchange chromatography? I think you have read this. Hardness of water. Hardness of water, when you have to remove the hardness, you have to use the ion exchange chromatography. You exchange the calcium ions by ion exchange chromatography. But let me just I'll have to tell you what is this ion exchange chromatography. But right now, just think of this, that we have basically given some parameters: molecular weight, separation techniques based on molecular weight. I said there are two. One is called gel filtration. Another is called SDS page. Okay. If it is based only on solubility, then we have techniques what are called salting in, salting out. Okay. If it is based on charge, we have ion exchange chromatography. Or there is something called isoelectric focusing. Isoelectric focusing. And when you have, what was the other point? Molecular weight, solubility, charge, affinity. Then we have a technique called affinity chromatography. Okay, so we will discuss all these techniques. Okay. First, let us consider solubility. Solubility is what that I said, that in presence of solutes, in presence of ionic solutes present in water, the solubility is affected. That solubility is affected, and this every protein is affected by different extent. See, first of all, why some solute, ionic solute, will affect the solubility of a protein. You have a protein here, and you are adding an ionic solute. Like again, ammonium sulfate is routinely used. Ammonium sulfate. As you add ammonium sulfate, and when you cross a particular concentration of ammonium sulfate, you see that the protein gets precipitated. Okay. On the other hand, think of the reverse situation, that you have water and you are trying to dissolve a protein. So not all proteins are very highly soluble in water. So the solubility is also varies. Some proteins are highly soluble, some proteins are less soluble. Okay. So suppose you are having a protein which is not very soluble in water. So what happens, that you take the protein and you add ammonium sulfate, you see that the protein goes into the solution. That means in presence of ammonium sulfate, the protein is going into the solution. This is what is called salting in. That means adding of salt makes the protein go into the solution. This is what is called salting out. That here it is, you have a solution of a protein in water and you are adding the salt, and after certain concentration you see the protein is coming out. The protein is precipitating out. So this is called salting out. Okay, so I think these two are clear to you. Nah? What is salting in? Salting in means that when some protein is not very soluble in water, so you can increase the solubility of the protein by adding little of the ionic solute. This is what is called salting in. For salting in, the important thing is that you have to, it generally happens when the salt concentration is low. When the salt concentration is high, then you see the salting out phenomena. Then you see the salting out phenomena. Okay. This has to be very clear. Salting in requires low concentration of the salt. Salting out requires higher concentrations of the salt. Okay. Now, why that happens? First of all, see, basically when you have proteins in water, so protein surfaces are what? Protein surfaces have charges. Protein surfaces, we know, protein surfaces will have charges because of the charges present in the side chains of the amino acids. So now if you add little salt, so what will happen? The charges, there will be ionic interactions. Suppose one side chain in a protein has, suppose I have a protein which looks like this. Suppose there is a positive charge here, there is a negative charge here, there is a positive charge here. So when I am adding ammonium sulfate, so the sulfate ion will have interactions, ionic interaction with this protein. Here the ammonium ion will have interaction with the protein. Here the sulfate ion will have interaction with the protein. So that means the protein is stabilized in solution. Okay. And that prevents two protein molecules. Say, how does protein precipitate out from solution, or any molecule? How does it precipitate? Precipitation is nothing but what is called aggregation. When molecules have to come together and form an aggregate. They come together, form an aggregate, and then finally come out of the solution. Okay. So when you have low concentration of the salt, what will happen? Because every strand is now stabilized by the salt, by the ions present in the salt. So it will not, the aggregation process basically makes it less soluble. Aggregation process makes the protein less soluble. The aggregation process will not take place because every strand is basically now they are neutralized. Their charges are neutralized by these ions of the solute. So what it says, that at low concentration, I can repeat what is written here. The added salt usually increases the solubility of the charged macromolecules because the salt screens out the charge-charge interactions. Screens out the charge-charge interactions. That means if you don't have the sulfate ions or the ammonium ions, so the protein strand will be like this. So there is a plus charge, there is a minus charge, there is a plus charge, and this protein has, suppose again similar, because it's the same molecule, same type of molecule, minus charge here, plus charge here, plus charge here. Now it will interact. They put one more minus charge here, one more minus charge here. It will interact. It will come together in such a way that the plus and minus are facing each other. Minus, plus. So that means there will be interaction between the unlike charges. The protein will come or interact in such a way that it is unlike charges which are facing each other, and that will aid the process of aggregation. Okay. So what ammonium sulfate is doing, it is basically making a screen. It screens out the charge-charge interaction. So this charge-charge interaction cannot take place because you have a screen of ammonium sulfate surrounding this protein molecule. Okay, so that's actually increases the solubility of the protein. This is basically nothing but saying the same thing. So at low salt concentration, the low salt prevents aggregation and therefore precipitation. On the other hand, when you add large amount of the solute, that means the salt, so what will happen? The proteins, again, another important point of protein is because they are charged molecules, so in water, they will be surrounded by water molecules. This is what is hydration. The protein will be hydrated. Okay, that happens when sodium chloride goes into solution. Sodium ions are hydrated, chloride ions are hydrated. So hydration will take place on the protein. Okay, this hydration also basically screens out the same thing. Hydration also does the same thing, but to a lesser extent. Hydration also screens out the charges on the protein, or it also prevents aggregation. If you have a hydration layer on a protein surface, so another protein layer will have also hydration layer. So now there will be less interaction between these two. So that means there will be less aggregation. Okay. Now when you are adding ammonium sulfate solid, as you increase the concentration, what will happen? Ammonium sulfate will now be, ammonium ions want to be hydrated. Ammonium ions will be hydrated, so also the sulfate ions will be hydrated. That's why ionic compounds go into water, because of the hydration. Okay. So what will happen now? The hydration, that means the water molecules surrounding the proteins, initially when you add small amounts of ammonium sulfate, there is no problem because water in large excess. When you are adding ammonium sulfate in large excess, now these hydration layer that will come out and hydrate the ammonium ions and the sulfate ions. So thereby making these protein charges exposed, and that will aid aggregation of the protein molecules. Again, I repeat, what is said here. At high salt concentration, the added salt lowers the solubility of the macromolecule because it competes for the solvent. As I said, when ammonium ions are more, sulfate ions are more, then it will take out this water molecule, which was hydrating the protein molecule, also utilize that for solvation of both the ions, ammonium as well as sulfate. So the protein becomes exposed, and so what will happen at high salt concentration? It removes the solvation sphere. The solvation means hydration sphere from the protein molecules, and they come out of solution because of aggregation. Is it clear to everybody? Okay. Now how can you utilize this for separation of proteins? Because different proteins have different extent of hydration. So different proteins will precipitate out at different concentrations of ammonium sulfate. Okay. If you have two protein molecules A and B, if A is more hydrated than B, then B will come out first as you add ammonium sulfate more and more, and you stop as you see that B is coming out. Then after all B has come out, then you add more ammonium sulfate, and finally A will also come out. Okay. So that is salting in and salting out. I hope this is clear. Any question here?
No, sir.
Okay. The second one, so that is the solubility. The second one is, let us go to this one, molecular weight. That how can you exploit the proteins? Different proteins have different molecular weights. Okay, proteins are big molecules, So that difference in molecular weight also could be very big. Here, what is done is not the chromatography that is done for organic chemists. Here, what is done is basically you take what are called gels. Gels means kind of they are consisting of beads, very small, tiny beads, also called resins, or you can usually you can call they are basically beads, tiny beads. You pack the column, okay, the glass column, suppose, okay. So it is filled up with all these beads, small beads, okay. Now, if it is beads, like look, think of marble, means that marbles are also spherical. So when you pack something with a marble, so what will happen? There will be always gaps. There will always be gaps between two marbles, okay. If it is extremely small powder, then the gaps will be almost non-existent. It is there will be no gaps. But if it is like a spherical, like this, marble-like, then what will happen? There will always be gaps between the marbles, between the beads. Now, it is not marbles. Ultimately, it is beads made up of special type of carbohydrates. Okay. So what will happen now? You pack a glass column like this with these beads, where there are spaces, empty spaces between beads, because they are spherical, so they cannot um, pack so tightly, uh, so that there is no empty space. There is empty space. Now what you do, you add a solution of protein from the top, okay, solution of protein from the top, and add more solvent, so that it ultimately comes down, and the solvent will, like your burette, uh, the solvent drops will come, ultimately will reach here, and you collect the drops. Now what will happen here, that because there are small gaps between these beads, so proteins which are small in molecular weight, if they are small in molecular weight, that means their size is also small. When the molecular weight differs, that means the size will also differ of the molecule. The sizes will also be different. So what will happen now? The small molecules, the small protein molecules, will now get entrapped into these small holes that are present. Okay. The large molecules, they will not enter into the gaps, because they cannot fit into the gaps. So they will, let me see whether there is a good picture I have. Just 1 second. No, not this one. It's not there. Uh, so small molecules will basically get trapped in the small holes that are created between the beads. Large molecules will not enter into these, or will not be trapped by the small gaps that are present here. It is only small molecules that get trapped. The large molecules will escape these traps and will come out faster from the bottom, will move faster, because they are not interacting in the gaps. They are not entrapped in the gaps between these beads. Okay, because of the large size. It's like means we can expand this view. It is, suppose this is the scenario, okay, and this is the column, okay. You are adding the solution of the proteins, okay. So the small proteins will, what they will, because they are, these gaps will fit to their side, so they enter this gap, okay. As it drops down, they see that another a bead in front. So now it has to take a route, a roundabout route to come to this way. Okay. So that means it is basically slowing down these gaps because it is going through the gaps between these beads. So it gets slowed down. On the other hand, the large molecules, they will not enter into any of these gaps. They will just pass through without entering the gaps, and they are the ones which will come faster. This is just the reverse of usual chromatography, that small molecules come faster than the large molecules. In this gel filtration, what will happen? The large molecules will come faster because they are not interacting with the small gaps that are present in the gels. It is, I can give an example, like there are two persons, A and B. Both of them go to a market. Okay. Go to a market. Now B has lot of friends who also come at the same time, similar time to the market. So there are many friends B has, say X, Y, Z. A is a very introvert person. He does not have much friends. So now B will, what will happen? Both have the same intention, ultimately buy the grocery or fish or whatever, vegetables, okay? And then ultimately come back to house. So now because A does not have, introvert, does not have many friends, so he will go straight, he or she, and then buys the thing and come back. What about B? B is actually what happens on the way to the market. What happens? Usually we meet friends, spend 5 minutes with X, spend 5 minutes with Y, 5 minutes with Z, and start marketing whatever is the he wanted to buy. Okay, and then come back home. So obviously, what will happen? Obviously, A will reach home, come back faster, much faster than B, because A is not interacting with anybody, or maybe one or two. But B has a lot of friends. So B is basically tied up with this XYZ, the friends XYZ. The same thing happens here. Small molecules, because there are a lot of gaps where it can fit, and so it will go there, go to the gap, fit for a few seconds, few minutes, and then later on, as more and more solvent you put down from the top, it will ultimately come down. Like for B, if it takes too much time, so he gets a call from the house, from home, that where are you? It is already 10 o'clock, you are not back from the market. So you have to now, okay, tell X that, okay, let me just go and then buy the things, okay. So basically what I'm saying, that the more you interact, the less will be, the more time you will take to do the marketing and come back. The less you interact, the faster you can come back completing the marketing. The same thing is the principle of this gel filtration, that larger molecules, because they are not interacting. Why they are not interacting? They are not fitting into the gaps which are created in the beads. So they will just go through straight away and come down here, okay, along with the solvent. Small molecules will be tied up and they will slowly come down. Their movement will be much slow. And some molecules will be, means if you carefully monitor that, you collect it, and you see that at some point of time you get proteins which have got a molecular weight of 50,000, that has already come out, leaving the protein which is suppose molecular weight of 20,000. If you are interested only with this protein, then you can stop. You don't have to run any further. That means you have basically excluded this 20,000 molecular weight protein to remain in the gel, and then you have excluded out, or you have isolated or separated the protein which has got a molecular weight 50,000 higher than this one. Okay, So this is the principle of gel filtration, which takes care of molecular weight. But all the time I was also talking about the size, because molecular weight is also reflective of the size of the molecule. So gel filtration is also called, another name is there, you can type your internet, size exclusion chromatography. Size exclusion chromatography. And companies have come out with different gels which have a cutoff. Some gels will be there where molecular weight of say 20,000, below 20,000 will all be stuck to the gaps that are present in between the beads. So that will be so that the company will say that this is a gel where there is a cutoff of 20,000, which means that the molecular weight, proteins with molecular weight or molecules with molecular weight less than 20,000 will remain in the gel, and the rest will come out of the gel. Okay, so you can have different grades: 20,000 cut out, 40,000 cut out, 60,000 cut out. See, now which gel you will be using, that depends on what protein you are trying to purify. If your protein has a molecular weight, the protein you are interested has a molecular weight of 65,000, okay, then you will go for a gel which has a cutout as close as 65 but less than 65. You cannot go beyond 65. Then that protein will also will be stuck to the gel. Okay, is it clear to everybody, this gel filtration? This is also called site exclusion chromatography.
Yes,
Any
sir.
any question here?
No,
No question. Okay, so basically it's quite, principle is quite simple. And so one which earlier in organic compounds, what was happening, it was interaction because of polarity, that polar interactions. Here it is size, which is important, because the gaps fits to the size of the smaller proteins, and larger proteins cannot fit into the gaps, so they will straight away come out from the column. Okay, so this is the standard way of getting these proteins of particular sizes, provided you know the size also. That is also, now if you have totally unknown mixture, how do you know what is the size of my protein, what type of gel filtration column I have to use? All these are done. All this can be indirectly, you can tell from other experiments that what is the molecular weight of my intended protein. Okay, I'll talk about that. Okay, so we have now talked about molecular weight. We have now talked about solubility. Now we have to talk about the how to explore molecular weight. There is another one, STS page, and charge. Actually, charge is also, I should write here, isoelectric focusing, and also page. What is this? What is this page means? And I will talk. Page means polyacrylamide gel electrophoresis. Okay. What is electrophoresis? I told you electrophoresis is nothing but movement of the movement of a macromolecule. Not only macromolecule, maybe amino acids also you can do, but usually it is macromolecules. If you subject a macromolecule which has got some charges, positive or negative, whatever charges, and if you subject them to an electric field, suppose this molecule has positive charge overall, and subject to an electric field where this is the negative electrode, this is the positive electrode, and this is actually placed on a on a gel, on a gel, jelly-like thing, okay, quite transparent, but also quite stable. It's fragile, but there is a definite way of making this gel. This is not very solid. This is kind of a jelly-like thing, okay, where you put the protein solution at the protein, and then the protein, because of the charge, if you apply electric field, that moves, that slowly moves, and this movement will depend on this movement. First of all, this process is called electrophoresis. Electrophoresis is basically the movement of these of a positively charged macromolecules in under an electric field, and this is put on a matrix, on a gel matrix. The protein is present on a gel matrix. See, the gel matrix is not very solid, it's kind of a semi-solid. Again, I said that it is a gel-like thing, jelly-like thing, which allows the protein to move. Because if it is a very solid, if it is extremely hard material, the protein will not be able to move through this matrix. So the matrix has to be very soft, should be jelly-like appearance, semi-solid type appearance, and so that the protein can move as you put the charges. Okay, so this process is what is called electrophoresis. Now the question is, what controls this movement? How much the protein will move? That depends, of course, how much time you are doing this electrophoresis. If you do it for 2 hours, the protein may move up to that point. If you do it up to 1 hour, the protein may have moved up to this point. Okay, so time is definitely important. But if you have two types of proteins, different types of proteins, which differ in charges as well as molecular weight, okay, then what has been found that the movement is actually dependent on E by m value. Means what is the charge per unit mass? That is important. Suppose the protein has a molecular weight of 5,000, say, and it has got a net charge of, say, plus charges, 5 plus charges. Okay. Another one, a protein which has got a molecular weight of, suppose, 20,000, and it has got a net charge of, say, plus charges, 60 plus charges. That means the protein is like this. So there are 60 plus charge points like this. Okay. So now, which protein will move faster? Usually smaller proteins move faster because of the molecular, because it is more, it is light. So light things moves faster than the heavier things. But here it is basically charge is important. That how much charge also you have. You have more charge here. So it is expected that this will move faster. But the higher molecular weight will try to make it move slower than this one. So that's why you have two factors connected with each other. Basically, you should have that what is the charge per unit mass. That means here 5 by 5,000. So the charge will be about, this is one way of estimating. I am giving you a rough way of estimating the mass to the electrical E by m value. So here it will be 60 by this. So how much that will come out? That will be 1 by, this is 333, right? Around something like that, 0.3. So you see which one is more, this one is more. Okay. Because its E by m value is more, so that will move faster than this one. Although this has got a light molecular weight, less molecular weight than this one. But the charge is more here. So there are two factors. Movement depends on charge. As the charge increases, the movement will be higher. So directly proportional. And the movement is inversely proportional to what? molecular weight. So that's why theory of joint variation tells that the movement will be proportional to E by M. Okay. So E by M will ultimately decide that how that will move. Okay. Now the protein, what happens? The protein is a really big molecule, and ultimately the the total charge surrounding the protein will not be very high, because the charges only come from what? Carboxylic acid or histidine or lysine. So it all depends how many histidines, how many lysines you have, or how many carboxylates you have. Uh, so compared to the number of amino acids, that are 20 amino acids, number of polar amino acids are how many? See, two glutamic acid and aspartic acid, and then lysine and arginine. So only four. So the overall charge of the protein may not be very high. So the E by M value will not be very high. It may be very low. So if the E by M is very low, then the movement will also be very slow. The movement will also be very slow here. You understood this point? The overall charge in this molecule, the protein molecule, is not very high. Even if you have different pHs, the total charge will never be very high. So you have to either give very high voltage so that it moves faster, or you have another option. Okay, another option is that you surround this protein molecule with an ionic, which is called a detergent. You know what is a detergent? Like this sulfonate. We have all these detergents today, Ariel, Surf, all these things. So they are basically what? R SO3 minus Na plus. R is a hydrophobic chain. Okay. Now there is a molecule called SDS. Who knows the full name of SDS? Sodium dodecyl sulfate. Sodium dodecyl sulfate. That means there are 12 carbons here. SO3 minus Na plus. Okay. So it's a hydrophobic one. Okay. That is commercially available, and these are used in our as a detergent. Okay. So the same detergent, if you add to a protein, this SDS, what happens? The protein molecule, usually protein molecules are what? They have a folding pattern. They are folded in a particular form. That is the 3D structure. In presence of SDS, it opens up, and then it is totally covered by SDS. The whole surface is covered by SDS molecule. Okay. So whatever protein you have, suppose you have a protein of this much length, say 10 amino acids are there, 10 amino acid containing peptide. Okay. And you have a peptide of say 20 amino acids. Okay. You have a peptide of 20 amino acids. If you are not adding this SDS, then it will have some charges at a particular pH. That will also have some charges. And again, I repeat, the total charge will not be very high. It all depends on how many basic or acidic amino acids you have in this peptide. Suppose this peptide has only one basic amino acid, so which will be present as BH plus. Only one positive charge in this 10 amino acid containing peptide. So, and on the other hand, in the 20 amino acid containing peptide, suppose you have only you have only one BH plus, only one positive charge. So the total E by M value will be very low. So their movement will be very low under these electrophoretic conditions and in the electrophoresis. But if you add SDS now, so this molecule will be now surrounded by SDS. SDS is basically having a negative charge in the hydrophobic side. So all these protein molecules, this peptide now will be surrounded by HDS throughout the surface. So 10 HDS molecules, 1, 2, 3, 4, 5, 6, 7, 8, approximately I said about 10. So the surface will be covered by each, if I say each amino acid is interacting with one HDS molecule, so so it will be covered by 10 HDS molecules. Okay, so there will be what? 10 negative charges now, 10 negative charges, 10 amino acids. So what will be the E by M value? You know, amino acid, I think last time I said amino acid has an average molecular weight of 110, average. So 10 amino acids means 1100. So the total E by M will be 10 by, total E by M will be 10 by 1100, right? That means 1 by 110. That is the E by M value. For the other one, which 20 amino acids, this will also have 20 HDS molecules surrounding it. So what will be the E by M value? So 20 divided by, now what will be the molecular weight? 20 into 110, because 20 amino acids, average molecular weight 110. So that makes it 1 by, so 10 by 1 by 110. So again that comes to 1 by 110. So that means these two molecules, their E by M value is same. Their E by M value is same. Okay. What is their difference? So now their E by M value is different, same. So now they will move, definitely. They will move, but they will move as per their molecular weight. Now only molecular weight, the molecule which has got a higher molecular weight, that will move slower than the compound, than the molecule which has got a lower molecular weight. Okay. So this is what is called SDS page. Again, I repeat, this is very important if you want to do any biochemistry experiment. What you do, that if you take the protein molecules and then you add SDS, the protein molecule becomes unfolded and it will be covered by SDS anions. Okay, so that now the charge, basically unit charge per unit mass is same for both the proteins. So only deciding factor for movement of the proteins is now only mass. So higher molecular weight will move slower, lower molecular weight will move faster. Okay, I think there is a picture. I have a possibly I have a picture of, where is that? Okay, this is how the electrophoresis is done. Electrophoresis is done. I used to have a video of this. Say this is the gel that I was talking about. See, this is quite transparent. It's very soft, and there is this is cavity here where you add your protein solution. Okay, and then there are electrodes which are connected. There is one electrode here, another electrode on this side. Okay, after you add the protein, you put the power on and the protein starts moving. Okay, the question is, there is one point, that how long you will continue this, because you are not seeing the protein solution, they are not colored. So what we have a reference molecule which is a dye, and that dye moves faster than all the proteins. So that dye will move, and that you can see with your own eyes. So when the dye comes here at the end, almost at the end, you stop the electrophoresis and then take this gel out. Now you have to see where are the proteins. Okay, how do you visualize in the TLC the organic compounds? If you have done in TLC, how do you visualize the organic compounds? Where it is in the silica gel plate? UV is one, that is correct. Under UV, if one is UV active, another is not, or if they give fluoresce differently, that is one. And the standard technique is earlier spray. You spray iodine, and wherever there is compound, that will there will be a spot, there will be a brown spot. Okay, so either UV or some spray, okay, which gives color. Iodine is absorbed by most of the organic compounds. So when you spray iodine, wherever there is compound, that becomes brown. Okay, gets the iodine color. So that's how you locate where is your compound. Here, in case of there is again another dye, which is called Kumasi blue. There is a dye which is called Kumasi blue. Kumasi blue. Is the spelling correct? Can anybody check? You have an internet access. Kumasi blue. If you have any internet access, what is the spelling? Kumasi. Is it only ends I? Kumasi blue. You have internet access. Definitely you have. But can you access with your mobile quickly without disturbing the MS team? I can actually type also. I have the mobile with me. It is IE. So you have I and then the first one, IE. Okay, IE. So you have, this is actually a blue dye. So what you do, you take this whole thing out, put it in a solution containing this blue dye, okay, and then take this dye, this out, and put it in another solvent, which is usually acetic acid, some cocktail, and after some time you take this gel out, and what will happen, you will see the gel will look like only wherever there is protein, you will see blue bands, not red. This is, I'm using red pen, that's why it looks red, but actually you will see blue. You will see blue bands. Let me see if I have any picture of that. Achha, this is the one which I was telling. See, this is your protein, which is in the folded form, and these are all SDS molecules. So what will happen in presence of SDS? It is slowly becoming unfolded, and after a few minutes, this is the picture. It is now totally unfolded, and it is surrounded by the negative charge of the SDS. So it doesn't matter what is the length of your protein. The E by M value, that means the charge per unit mass is same. So ultimately it is only the molecular weight, that means the molecular weight of this whole system, that will determine how much the protein will move. Okay, so this is what is denaturing. This is what is called the SDS page electrophoresis. Okay, SDS page electrophoresis. It's routinely used. It is routinely used to separate proteins, and as I said, that when you do size exclusion chromatography, you have to have an idea what is the molecular weight of your protein. Okay, so suppose this is the gel. Again, I go back here. This is your gel. So what you do here, only there are two groups. You can actually in one group you have your protein mixture. In the other group, the companies give you a cocktail of mixture of proteins with definite molecular weight. These are called molecular weight markers. Okay, so what will happen, that when you develop the plate, develop means, as I said, you put in Kumasi blue, then wash, and then see you can see it with your own eyes. You don't have to shine UV or anything. if you do that, yes, this is the picture. If you do, see, this is a gel picture of, there are 5 lanes here. Okay, so you see, there is protein here, there is protein, a small amount of protein here, there is a protein there. So it's a, so many protein bands you can see. Okay, what is not present here is actually in, you actually put another lane where you add molecular weight marker. Molecular weight marker. Okay, molecular weight marker means it's a mixture of different proteins with known molecular weight that is actually supplied by the company, and you know that it will give different bands, and you know what is the molecular weight of these bands. The company will tell you what is the molecular weight of all these bands. Okay, so now what you do, if I ask what is, suppose you are interested in this protein and not the other ones, so what is the molecular weight of this? So what you do, you try to, you see that it is in between these two. So you have an idea now that what could be the molecular weight of this. Suppose this is say 50,000. Always the slower ones will have higher molecular weight. So suppose this is 100,000. Suppose this is 80,000. Okay. Suppose this is 60,000. Suppose this is 40,000. So you can now tell what is the molecular weight of your target protein. Actually, you can, this is a logarithmic scale. It is not like that. This is basically what is called logarithmic scale. But at this point, you can just tell that at least I know that the molecular weight of my protein is above 40, but less than 60, because it is in between 40 and 60. Okay, so that's how you actually get an idea of the molecular weight of your target protein. Okay, is it clear? This is SDS page is very important. There is one problem with SDS page, is that, what is the problem? Because you are actually, what is denaturing condition? What is meant by denaturing of protein? The classic example of denaturing of protein is you take the egg and then boil it, and what you see, the whole thing becomes a solid. The egg white is actually a protein, albumin, ova-albumin. So that becomes, it's the same protein, but that is totally denatured. Earlier it was like a, what? It's a transparent kind of a jelly-like liquid, and then when you heat it, boil it for some time, it becomes a solid. So basically what happened, it is denatured. It has lost its three-dimensional structure and becomes denatured. So denaturing of protein is basically what, that you lose the activity of the protein. So when you do SDS page, what you are doing, you are actually taking this is the actual nature, the protein under the native condition. Native condition means when it is active. And then as you add SDS, you are disrupting all the intramolecular hydrogen bonds, all electrostatic interactions, hydrophobic interactions, everything is disrupted. And you ultimately get a protein which is denatured. So SDS page is also called electrophoresis under denaturing conditions. So the disadvantage is that if you isolate this protein, you will not get any activity from this protein. You can isolate from here because this is a gel. You cut it out. You cut it out with a scalpel, okay, or with a knife. This piece, put it in solution, isolate this protein, but you will not get any activity. Why? Because you have done it under denatured conditions. Your protein has lost the three-dimensional structure. Okay, that is important, or it has lost its native structure. That's why this naturing and denaturing, that word is there. Now some proteins you can get it back to the original form, the native form, but for many proteins it is not possible. Like egg white, if you boil, it becomes white, solid. Now can you get it back again to the white in the original egg white? Not possible, because the protein is totally denatured and it is irreversible. In many cases, however, it is reversible also. If you heat a protein or if you subject a protein to a different pH, remember this three-dimensional structure of a protein is present only at a certain pH, at a certain temperature, at a certain salt concentration. All these are important. Okay, so if you suppose heat a solution of this protein, it will be denatured. If you cool it, again it can go back to the original conformation. So that is reversible. Naturing, denaturing process is reversible. But for some proteins, it is not possible. So one possible disadvantage is for SDS page is that you are losing the activity of the protein. Unless again, if it is reversible, that you can again reconstitute the three-dimensional structure. If it gets back to the three-dimensional structure, that is okay. But usually, after electrophoresis, it is not possible to get it back into the original reactive form. Okay, is it clear? This is the SDS page. So here it is basically you are utilizing both the molecular size. That's why it was put under. When I started, it was put under SDS page under molecular weight. Why? Because ultimately charge does not matter in SDS page, because you have uniform charge to mass ratio by adding the SDS page. Okay, any question? These slides you have to go through. I am not covering all the slides. This is the ammonium sulfate precipitation method. That different proteins are precipitating at different concentration of ammonium sulfate. So I think if you go through the slides, you will understand what it is being said. So I'm not covering everything. Yes?
Sir, can you upload all the slides?
All the slides. Actually, this is starting from the, let me see. This is the one. I actually don't change I just continue from the very beginning. So there is only one. So we started with this. What is the syllabus? So I just continue adding one after another. So the whole, this is only one file. So that I have to upload.
Yes, sir.
Hopefully it will not be that big, because I just add on one another. It is not that day one we have one set of slides. It's just a continuity. So which is good in one sense, that you have everything in one file.
Yes, sir.
Okay. I think one more thing I want to talk about is this affinity chromatography. So we have done what? We have done the salting in, salting out. That was mentioned in your syllabus. And we have done the gel electrophoresis, the SDS page, that is that we have done, and I think these two, and gel filtration, or what is called size exclusion chromatography. The fourth one is what I should cover is affinity chromatography. Affinity chromatography is not very difficult to understand. It is basically again like gel filtration, very similar to gel filtration, but here it is made up of a gel, which is connected. These gels are special gels, which is connected to a ligand, to a molecule, to a small molecule, which actually interacts with one of the proteins that you have. Remember that the proteins, what are the functions of proteins? If I ask you after all these classes, what is the function, what are the different functions of a protein in the body? Can anybody start? 1, 2, 3, 4. What is the first function of a protein in the body? Or do you think most important function of a protein in the body?
Then it acts as enzymes.
Enzymes, okay. So catalysis. So
Yes,
one is
sir.
one is the catalyst. Big area is catalysis. Then proteins can be also receptors. Receptors means
Yes.
receptors like you have heard of neurotransmitters, that sometimes you feel good, sometimes you feel sad, sometimes you feel depressed. Now there are a lot of medicines available to make you feeling feeling good. All these things are available today, but that is actually what happens, that there are cells where the surface there are proteins, and these proteins are called receptors, where small molecule binds. There is no reaction as such. Small molecule binds and creates a signal. That signal is transmitted. Okay. So that is called receptor chemistry. So it could be enzymes, it could be receptors, it could be structural proteins like the collagen, hair, the muscle. Those are made up of proteins also, but they are structural proteins. They maintain the structure. Membrane proteins, they maintain the structure of the cell. They can be hormones also. Insulin. Insulin is a hormone. There are many hormones which are made up of proteins. Okay. So proteins are of different types. So when I say you are separating proteins, it may be that the proteins could be receptors or could be enzymes. Why I bring these two? Because these two are the ones which has got what is called active site. Because the proteins have a particular definite geometry like this, so also receptor, where small molecule goes and binds, and then reaction takes place if it is enzyme. If it is a receptor, no chemical reaction, but it sends a signal inside the cell, and the cell starts doing something. Okay. So they have a cavity which is called active site. Okay. So in affinity chromatography, what you do basically, if you know some molecules which can bind to the cavity, so then what you do, you make a gel where you attach that small molecule L, usually called a ligand. Okay. So you attach L to all these beads. Okay. So when you add a mixture of enzymes from the top or receptors, what will happen? The enzyme which is recognizing or which is having active site where the L can bind, so that enzyme will get stuck to this gel, and other enzymes will come through, right? So this is what is called affinity. That means you are making the gels to have affinity with one of the enzyme or one of the protein. Here enzyme is the example, one of the protein in the mixture. So that gets stuck because of the affinity with L. Okay. So other proteins go through. So when everything goes through except the enzyme of your interest, now what you do? After all this, when L goes inside, the interaction of L with this active site are all weak bonds, not strong bonds, no covalent bond formation. All are weak bonds. Okay. So you can now elute, you can put a solvent which is called eluent of higher polarity. So then what will happen? If you use higher polarity, L will now come out from here, and L will come out of this, and this higher polar solvent basically is displacing this L, and that will now slowly come out of the gel. You understood this point? Initially, you attach a ligand which has got complementary binding site of a in the protein, in one of the protein. You add the solution of the protein. So that protein which has complementary binding site with L, that will get stuck to the gel. Once all other proteins are eluted, then you add a solvent of gradual. Solvent means usually it is a buffer, buffer of different pHs, because changing the pH means you are changing the polarity of the solvent. So as you change the polarity slowly, one by one, ultimately what will happen? This L will, the protein will come out of L. Okay, the protein will have more interaction with the solvent than L, and then it will come out slowly, and it is released, and it will come out from the bottom. So that means you get the protein. If you are lucky, you can get protein very pure. If you are not that lucky, that there could be other enzymes which have some partial interaction with L, that is possible. Then also you can get, but at least a majority of the impure is other unwanted proteins that will come out by this process. So this is what is called affinity chromatography. This L can be of different types. You know what is antibody? What are antibodies? That when a foreign, you know that when a foreign molecule enters, we generate antibodies, which are actually proteins. Okay, so if you want to separate antigens, or if you want to isolate antibodies, the reverse one, if you want to isolate antibodies from a mixture, so what you do? Antibodies are generated due to the presence of an antigen, which is the foreign molecule. So you attach the foreign molecule antigen here into the gel, okay, and then add the mixture of antibodies. Okay, add the mixture of antibodies, and the antibody which is complementary to this antigen, that will bind, others will remain here, and then once everything has gone through, then the same thing, you add solvents of different polarities, and ultimately you get your desired antibody. Okay, so there are many ways of finding whatever you should attach to the gel. Okay, it could be an antibody, it could be an antigen. If you are isolating antigen, then it is to be antibody. If you are isolating antibody, then it should be an antigen. If you are isolating an enzyme, then it should be the substrate of the enzyme. So lot of possibilities here. So it has got a huge scope, this affinity chromatography, right? And only problem is this is little bit expensive, because to get the gel attached to the ligand, that makes it costly. But today, actually, what happens if you get a very tiny amount of the enzyme or the protein, that is enough. Enough means there is a process. This is not in your syllabus. There is a process which is called. It could be in the syllabus, other modules. I don't know. There is a process which is called cloning, gene cloning technique, where you can now any protein can be made in large amounts by a process called gene cloning, or cloning of genes. Like insulin, insulin. Who uses insulin? People with insulin dependent diabetes. No? They have to take these insulin shots. You know that, no? Insulin. I think now diabetes is almost in every house. There will be someone who is a diabetic patient, and some people take medicines. Some people have to take insulin shots. There are different types of diabetes. Diabetes 1, diabetes 2. One is insulin dependent. Insulin is not being made by the pancreas. The pancreatic cells are basically dead. So they have to take insulin. When they take food, they take a injection of insulin. Okay, these are available. You take it. You have to take it. No? Because every day you cannot call the pharmacist to come and then give you the injection. The injection is very easy. So they take the injection of insulin. Okay. Earlier, now where do you get insulin? Question is, there are so many diabetes people. So you need grams and grams of insulin. Where do you get the insulin? Earlier, insulin was obtained from, actually insulin is required by every animal, not only human. Cow needs, goat, everywhere. So they found that the insulin of cow, that means bovine insulin, bovine relates to cow. Bovine insulin is very similar in structure to the human insulin. Okay, because there is some difference in insulin isolated from goat, from other animals. Okay, but fortunately they found that the cow insulin is very close to the human insulin. So earlier people used to take insulin isolated from cow, but that's not a very good way. Now you have to slaughter the cow, you have to isolate the pancreas and get the insulin. So there was a lot of problems. But you have many issues. First of all, you are just killing the animal. That is number one. So you have to create number of animals. Okay, the population. You have to maintain the population. Number two is that there are also other issues, many religious issues also that come into play. So fortunately, in the late 1980s, this gene cloning technique was discovered, and now there is no problem. Insulin is isolated from a bacteria. Okay, I think that is another story. Biochemistry actually is so interesting these days. If you are reading organic chemistry, but never neglect this biochemistry or biology. This is organic chemistry is intimately tied up with biochemistry. Okay, so affinity chromatography is clear to everybody. I gave only some examples, some basic idea. Yes. Tell me. Yes, you want to say something? Who is that? Go ahead if you want to say something. No? So this is clear. So we have now covered all the things: affinity, the separation based on charge, separation based on molecular weight, separation based on solubility. There are still other techniques. I think it is then the whole thing becomes, there's no end to it. There are so many other techniques which are possible, but these are the four basic ones which everybody should know, that these are the ways to do it. You have a by the way, project, any project in your last year, in your final year, MSc project?
Yes,
Yes,
sir.
sir.
And you are all doing the project. Is it in the last semester or
Yes, sir.
Semester.
Last semester.
now it is the last semester, final semester? You are in the
Yes, sir.
final semester, so you are all doing some project. Now
Yes, sir.
this year is very difficult to do any experimental project. It is
Exactly.
not possible. Yeah, it is not possible. So only thing what you can do, you can only write up what we are doing. We are actually asking them to write a review article.
So we are on campus since March.
Oh, you are in campus now.
Yes, sir.
That's good. Oh, I didn't know that. But are you doing any experimental work, or you are all doing project
The
on
few of them are doing experimental and few are doing computational.
or computational. So that's
Yes,
good.
sir.
Yeah, this is another way of learning techniques through projects. Yeah. I don't know whether you have done any project in summer earlier at the fourth year
Yes, sir.
level. You have done, no?
Yes, sir.
Anybody has done any has joined any biochemistry lab or no?
No, sir.
No,
So,
no, that's okay because it usually people people are very reluctant to take the summer training, but now there are a lot of fellowships also available. There are plenty of scopes to do summer project. But now we are in the final year. You are doing the MSc project. That's fine. But what I am saying that if you are um, means as a basic chemist, especially organic chemist, one has to learn the basics of biology. I don't know whether you have this molecular biology in your syllabus, little glimpse of molecular biology. That would have been really helpful. But I don't know. I have not seen the entire syllabus of your course. This is only one module. The peptide chemistry. Uh, in our IIT, we have an entire course, not module, entire course on biology, organic chemistry and biology. Then you have all the drugs. You have any course on drugs and drug discovery, medicinal chemistry?
No,
Maybe
sir, we don't have.
you don't have. Yeah, maybe I can talk. I can recommend all those. Yeah, that at least your
Yeah.
uh, this, this later students will be benefited. So that is actually all the. Okay, this is the basic principle of affinity chromatography diagrammatically. This is easy to understand. This is the gel. Attach the ligand. Ligand has a particular geometry. You add the proteins. So this is the protein. Other proteins they are not showing, but they don't have complementary geometry. So it has got complementary geometry, got stuck. Other proteins come out, and then you have to add a solvent, and so that this protein comes out, and you isolate that. So this is the principle of affinity chromatography. Okay. In your syllabus, I think there are. Okay, this is the general protocol. I think we have all salting out. This is gel filtration. That is also uh, we have covered. SDS page we have covered. And okay, what is again isoelectric point of a protein?
neutral pole.
Neutral.
You,
Okay.
no
Uh,
charge.
there was a question. Actually, no charge. The two charges counterbalance. Overall, there is no charge here. You have to say overall.
Yes, sir.
Overall, there is no charge. Okay.
Yes, sir.
The question is how to determine the isoelectric point of a protein. It's very difficult. Amino acids, there is a formula. If you know that half pK1 plus pK2. If you go back to the physical chemistry, you will see that isoelectric point of an amino acid is half of pK1 plus pK2. pK1 is the basically dissociation of the carboxylic acid to that is the pK1, and pK2 is the dissociation of the ammonium NH3 plus to NH2. So if you add these two pKs and divide by 2, you will get the isoelectric point of amino acids. But for proteins, very difficult to calculate uh, to really determine the isoelectric point. But there is a very simple way of doing it by what is called isoelectric focusing. See, what is done basically, if you do the same electrophoresis on a gel, remember in protein the electrophoresis is actually, whether you have noticed that, it is actually done from the top. Unlike our thin layer chromatography, we do it from the bottom. That migration takes place uh, with the solvent. Here, the protein comes down from the top. Okay, that is the way they describe the gel. Okay. Uh, Now what happens if you have a gel where you have different pHs at different regions. Okay, so you bisect it, you dissect it, not bisect, dissect these different zones. Suppose this is pH 1, this area is pH 2, this is 3, this is 4, this is 5, 6, 7, 8, etc. Now you start doing the gel electrophoresis. Okay. So protein, suppose the protein is neutral at pH 5. So what will happen? The protein will start moving under the electric field, and at pH 5 it will stay there because it is neutral here in this pH range. After that it will not move. So what is your job? You will just develop it and see that which pH area this protein band is staying, is residing, and that is its isoelectric point. You understood it, no? Basically, the gel has to have a pH gradient so that it moves and then it stops as soon as it assumes a overall charge is 0. So it stops there. So this is a nice way of making the, this is also called isoelectric focusing. Means basically you are actually focusing. It's in a mixture, but ultimately you pinpoint the protein of interest. So that's why this name is given, isoelectric focusing. I think this is written here. Now it can be predicted. They have some calculation, of course they can do, but that is quite difficult for proteins. It is determined experimentally by techniques such as isoelectric focusing. This is what is, the protein is placed in a pH gradient and subjected to an electric field. The protein moves up to its pi. Okay, so that's how you know what is the isoelectric point of the protein. Okay, and by isoelectric, if proteins have different isoelectric points, which is also very important to another important parameter, because last time I was a little bit in a hurry, that suppose there are 3 proteins A, B, C. This has got an isoelectric point of 4.5. This has got an isoelectric point of 6.5, and this has got an isoelectric point of 8.5. So if you do, how to separate this? You already have all the size exclusion, all these things are there. But there is another nice way of exploiting the isoelectric point, that here in the middle you spot it, the mixture of proteins. Suppose there is plus charge, plus electrode here, minus electrode here, and you maintain the pH of this whole matrix at 6.5. Then what will happen? Both C and A will move, but B will remain stationary. Okay. Now the question is which direction A will move and which direction C will move. Can anybody tell? Which direction A will move, which direction C will move. So you have to have the very basics, that isoelectric point pi, P is small actually. So if a pH is greater than, suppose the isoelectric point take a value 4, okay. If the pH is higher than 4, and if the pH is lower than 4, what will be the charges on of the protein? So if you cross the pi, what will be the charge of the protein? Plus or minus overall?
Plus.
See, there is, I think I always faced this problem when I was a student. But what I used to do, I used to take an amino acid just to make myself very clear. See, this is what is glycine. Okay. So at low pH, glycine will have, this is protonated, this is also protonated. So as you raise the pH, what will happen? You will get NH2 NH3 plus, CO2 minus. First this will dissociate, and then as you raise the pH further, you will get what? NH2 and CO2 minus. So these are the three species. Low pH this, so at some intermediate pH this, and as you increase the pH, this is the one. Now this is the one which is the isoelectric, which is neutral, NH3 plus CO2 minus. Okay, so that means as you increase the pH beyond Pi, overall charge becomes negative. Never forget that, huh? And if the pH is lower than Pi, the overall charge is positive. Always take glycine. If you get confused, take glycine as the example and decide that if it is on the left side, that means if the pH is lower than Pi, it will be positively charged. The protein will be positively charged. If it is greater than, pH is greater than Pi, it will be negatively charged. So now you can tell which one moves where. B remains stationary. So A isoelectric point is 4.5, which is lower than 6.5. So that will remain as positively charged. Is it? Sorry, I am sorry, very sorry. Isoelectric point is 4.5. Your pH is maintained as 6.5. So you are maintaining pH above the isoelectric point. I am very sorry. Above the isoelectric point, you are maintaining the pH. So above isoelectric point, it will be negatively charged. So that means A will have a negative charge at pH 6.5, and C will have a positive charge at pH 6.5 because it is less than its Pi. Is it clear to everybody? This is minus, that is plus. So A will move towards this direction and C will move towards this direction.
No, sir.
It's not clear? Again explain. Okay. What I am saying, is this clear? The glycine case. This is glycine. So at low pH, highly acidic, NH2 will be protonated and carboxylic acid will also be protonated. It will not dissociate. As you increase the pH, first this will dissociate. CO2 minus, this will remain as NH3 plus. Then as you increase the pH further, this will lose the proton. So this will be NH2 CO2 minus. Okay. Now this is what is the species, the deuterionic. This is called deuterionic species or the neutral species. Okay. Maybe I didn't use the word deuterion. This is called deuterion. Means the existence of both plus and minus. So this is the form at the isoelectric pH. Okay, isoelectric point. So now if a pH is more than isoelectric point, it becomes negatively charged. If the pH is less than isoelectric point, it is positively charged. Is this clear to everybody? Pi?
Yes, sir.
This is clear, okay. So here it will be positively charged, here it will be negatively charged. Now you have a mixture of 3, ABC. 6.5, you are maintaining the pH throughout this gel, okay. So B is right at 6.5 Pi, okay. So it will not move, it will have zero charge overall. So B will remain here. Question is, what about A? What is the Pi of A? It is 4.5. What is the pH you have maintained in this gel? 6.5. So you have maintained a pH which is greater than the Pi of A. So if it is greater than Pi of A, then it is negatively charged. See 4.5, 6.5 and 8.5. These are the 3 PIs. You have maintained the pH of 6.5. So for A, you have actually crossed the Pi. You have crossed the Pi. Your pH is more than the Pi of A. If the pH is more than Pi, the charge will be negative. For the C compound, the Pi is 8.5. The pH you have maintained is 6.5. So your pH is now less than the pi. Less than pi means positive charge. Yes, someone wants to say something. Tell.
It's clear, sir.
Now it is clear?
Yes.
Yeah, sometimes when I was a student, I used to get confused. Hey, what is that? What is that? What is it? Yeah? But I think just think carefully. Think glycine as your example, and then come out to a conclusion. Okay. So by this, taking the PI issue, you can actually separate proteins. If the PIs are quite different, you have to maintain the pH at the proper level and then do it. You can separate the molecules. Okay. I think basically that's it. There are a few other issues which are there. I'll send the slides. They said that you have to know something about hemoglobin, myoglobin, then hemoglobin, myoglobin, and globulin and albumin. Okay, I will send these slides. Okay, and you go through these slides, and then we can have some doubt clearing session. And we can discuss these things. These are basically you just read it and that will be enough. There is nothing to uh, understand here. It is just information that is given for all these protein molecules. Of course, myoglobin and hemoglobin is very important. They are the oxygen transporters. Uh, but if you, as we can discuss it, we'll have one more extra class that will be a doubt clearing session. What I request you that once I upload this slide, I'll do right now. End show. So this is being recorded. Now I have to stop the recording, and then I can upload the whole recorded version also. Today's recorded version. Earlier ones you got the recorded version. Did you get the recorded version of the earlier ones?
Yes, sir, but it's only audio.
Only audio.
Yes, sir.
Okay. So I will now upload the video, this slides. If I upload the slides, files, right? Is it
Yes.
under class materials? Is it? If I do under class materials, something is there. Carbohydrate. No, not under. That is actually somebody else's. No?
Yes, sir.
So maybe I can just put.
Make a new folder.
Make a new folder.
Yes, sir.
How do you make? Files.
From new.
Oh, from new. Folder, right. So this is folder name is, suppose this is peptide chemistry. Yeah?
Yes, sir.
Peptide chemistry. Create. So peptide chemistry. Now I can open this up. Nothing is there. I upload that file. Where is that file? This one, and just now we have done. It may take some time. It is uploading, but the audio you have the audio now. Huh? So I don't have to upload anything. Okay, good. So what I said that I request you to send me the wherever you have doubts. So I compile those issues and then we will have one doubt clearing session. But that I will have to tell you when that is.
Yes.
Okay, sir.
because this is supposed to be 10 lectures. We have covered 10 lectures, but I think one doubt clearing session will be helpful. So let it be, I don't know how long it will take. Let it be uploaded. And if you have, I think already it is almost 7 o'clock. You will be possibly very bored and tired. So let us call it a day. Let it upload here. Once it is, it will upload by itself. So I don't have to do anything. I'll just keep it on. Let it do it, and then in the meantime you can just relax, go and have a coffee, because we didn't have any break today in between, because I wanted to cover the syllabus. Okay, so you send me by email your doubts. Okay, that these are the areas where I have doubts. Then I can compile and have the doubt clearing session.
Okay, sir.
Okay, sir.
Thank you, sir.
Okay, thank you then.
Thank you, sir.
Thank you. Let it just upload. Maybe I have to keep this on. The MS Team should be on if I want to. No, I can actually come out of the MS Team also. No, this I can cross out, leave, complete the meeting. See, that is our problem. We don't know computer very much. Leave here. Okay.